Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we are studying out of chapter 4 of our book, which is on heat effects, and we are working on heats of reaction. So, you've seen heat of reaction in chemistry classes and maybe in the mass and energy balance course. We need to, for this, define a standard state. It is defined as the state of a substance at a specified pressure, composition, and phase. Now, that's going to vary from book to book, but in this book, it means that for a gas, it's the pure substance as an ideal gas at 1 bar. And for liquids and solids, it's the actual pure liquid or solid at 1 bar. All of the conditions for a standard state are fixed except for the temperature, and really that should be the temperature of the system. But a lot of times we're going to find data at a particular temperature, and most frequently, as is for this book, it's going to be at 298 Kelvin is going to be the temperature that we find. Now, the standard state properties will be a function of temperature and only temperature. There are some facts you, again, should have seen in a chemistry course or something, but about heat of reaction. When you have an exothermic reaction, it releases energy, so energy is going out of the system, and an endothermic reaction is going to absorb energy. It's going to take energy in. These are going to, in general, if you have an exothermic reaction, you're going to notice it generally heating up a little bit, and an endothermic reaction will cool off a bit. At low to moderate pressures, we're going to see that heat of reaction varies with temperature and only temperature. And the quantity of this heat of reaction, the value of it, is going to depend on exactly the way we write our reaction. It's based on 1 mole in the reaction, something with a stoichiometric coefficient of 1. So if you write a reaction with a different stoichiometric balance, so for instance, if you said A molecules of A plus B molecules of B makes C molecules of C, then it's per mole and there are A moles in the reaction. If you were to do this so that you had fractional quantities, I could have something like this where now then my stoichiometric coefficient for A is 1. And this is going to be different as I do this. So it's going to be like a kilojoules per mole of reaction, whatever is meaning 1 in your reaction. The other thing you need to know is that the value of the heat of reaction will depend on the phase of each component. So if in the first reaction I had compound C was a liquid and in the other one it's a gas, I would expect very different values for the heat of reaction because I have to vaporize the substance to get it to a gas phase. Most of what we know is based on HESS's law, which says that if the stoichiometric equation for reaction A could be attained by the algebraic combination of reactions B, C, whatever, then the heat of reaction can be found by performing identical algebraic operations on reactions B, C, whatever. So for instance, if you have a reaction carbon plus oxygen makes CO2 that has heat of reaction number A, and carbon monoxide plus half of an oxygen molecule makes CO2 with heat of reaction quantity B, I can use these to figure out the heat of reaction for how carbon and oxygen react to form carbon monoxide. So one way to think of that is that C plus O2, the first reaction, makes CO2, and from the second reaction, CO plus 1/2 O2 makes CO2. If I subtract on both sides, then I've done the same operation to both sides, right? This is kind of an algebra thing that we've learned to do. And so when I do this, I get C minus CO plus 1/2 of an oxygen is 0. But if I move this to the other side of my equation, I end up with the reaction that we were looking for. So this is how I can algebraically combine reactions. So what does that mean about the heat of reaction? Well, the heat of reaction of this is going to come from the heats of reaction that I started with. I took reaction 1 and subtracted reaction 2. So that means I'm going to take the heat of reaction 1 minus the heat of reaction for 2, and so this will get me A minus B. Frequently, the reaction information that I have is formation reactions. So a formation reaction is the reaction that will form the compound from its atomic constituents. And it needs to be the atomic constituents in the form that they naturally occur. The heat of formation will be the heat of that formation reaction. And so, for instance, we make CO from C and O2, so C plus 1/2 an O2 will make CO. CO is a gas in nature, O2 is a gas in nature, carbon is a solid in nature. Similarly, H2O is going to be made from H2 plus 1/2 an O2. Both of these are in nature gases to make H2O, but I could do this as a gas, or I could do this as a liquid. And I expect a different value for heat of formation depending on whether I'm doing it as the gas or as the liquid. So it's going to be important to note the value of the heat of formation will depend on the phase of the molecule being formed. Now we do have data for heat of formation in Appendix C. This is at 25 degrees C or 298 Kelvin. And we combine this with HESS's law so that I can find heats of reaction for other reactions. So HESS's law, what it gives us is that the heat of reaction is the sum of all of the heats of formation of products times the stoichiometric coefficients from our reaction minus the heats of formation of all of my reactants times the stoichiometric coefficients for those. And in this case, this is where you see that depending on what my stoichiometric coefficients are, that's going to be why as I write a reaction in a different way, I will get a different answer. Now all of these, if my delta H formation data is at 298 Kelvin from my book, then this will give me heats of reaction at 298. If my reaction temperature is something else, then we will need to adapt that by cooling and warming my materials using C sub P dt to the reaction temperature. Another way that we can work these is using heats of combustion. Heat of combustion data is not available in our book, but it's available in a lot of other sources. A heat of reaction is the energy that is released when you react a substance with oxygen to form combustion products. In other words, you set them on fire. So the combustion products that we're talking about will be carbon dioxide as a gas, SO2 as a gas, nitrogen as a gas, water as a liquid, and any chlorine will make HCl that will be aqueous in that water. We are going to always need to make sure that we are aware that this is liquid water. If you have vapor water, you'll have to take that into account. Now again, we're going to do this with Hess's law, but so if I had like a hydrocarbon, let's go with just a simple methane, and react it with oxygen, I'll make some CO2, and I'm also going to make some water, and so I end up with this as my combustion reaction. Before I was doing like CH4 would have come from carbon plus 2 hydrogens. This would be a gas, this would be a solid. This is probably a gas, 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 and liquid. If I have all of those, then the problem is that for heats of formation, this was the product. Now then, this is a reactant. And so when I use Hess's law, or write Hess's law, we get the sum of reactants minus the sum of the products. And again, it's because of the way we write those reactions. Now, the water that's being formed is always liquid. If you have water as a vapor in your product stream, then you're going to need to vaporize it, and depending on where it shows up in your reaction, the stoichiometric coefficient times 44.01 kilojoules per mole, and add or subtract based on whether it's a reactant or a product. Okay, it's going to be positive when it's a product, negative when it is a reactant. So this concludes this little quick lesson on heats of reaction. We're going to be doing examples in class. Thank you very much for your time.